Welcome student. Today I shall discuss about the topic of general topology. First of all, what is topology? That means what is the meaning of topology? Topology is nothing but a composition of two Greek words. One topos, that means surface, and another logos, that means study. So basically topology is nothing but a study of surface. Let's do this. Before going to the discussion of topology, we first introduce the definition of a power set. Let X be a non-empty set, then the family Px of all subset of X is called the power set of X. For example, if X is equal to ABC, that means a set consists of three elements, then its power set is phi, singleton A, B, C, and doubleton AB, BC, CA and X. Note that if X consists of n elements, then the power set consists of 2 to the power n elements. If n is equal to natural number, that means the set contain element of 1, 2, 3 and so on, then the power set is obviously uncountable. Now we are going to the definition of topology. Let X be a non-empty set and tau is a subset of power set of X. Tau is called topology if tau satisfies the following condition. First condition, phi belongs to tau. Second condition, X belongs to tau. Third condition, the union of any collection of subsets belongs to tau, also belongs to tau. And finally, the intersection of any two subsets belongs to tau is also belongs to tau. Then tau is called a topology on X and the pair X comma tau is called a topological space. Now we introduce the definition of open set. Let X tau be a topological space. Then the member of tau are called the open sets in X. For example, let tau is equal to phi comma X. Then it is obvious that it is a topology and this topology is called trivial or indiscrete topology on X. Next, if you choose tau is equal to power set of X, then it is also forms a topology and proof is very simple, so omitted, and this topology is called discrete topology on X. Next, we consider a set consists of three elements, that is ABC, and tau 1 is equal to phi, singleton A, doubleton AB, AC and X. We easily show that tau 1 is a topology on X, and again tau 2 is defined as phi, singleton A, doubleton BC and X. Then tau 1 and tau 2 forms two different topologies on X. It is generally possible to define different topologies on any given set X and thereby obtain different topological space on the set X. Next we introduce a very important topology and that is called cofinite topology. What is that? Let X be a infinite set and tau is equal to phi union all such A such that X minus A is a finite set. Then first condition is obviously satisfied because phi belongs to tau, and condition 2, X minus X is equal to phi and phi is a subset of every finite set, so X belongs to tau. For the condition 3, let A alpha belongs to tau and alpha belongs to index set. Then all X minus A alpha is a finite set because A alpha belongs to tau. If A alpha not equal to 0, not equal to phi, then X minus A alpha is a finite set. Next, let X minus set union alpha belongs to delta A alpha is equal to intersection alpha belongs to delta X minus A alpha. It is elementary set property. So proof is very simple, and this is subset of x minus a alpha for every alpha. Because the right hand side is a finite set, so x minus union alpha belongs to delta a alpha is a finite set. Thus union alpha belongs to delta a alpha belongs to tau. For the condition 4, let a1 a2 belongs to tau. That means x minus a1 and x minus a2 both are finite sets. So x minus of a1 intersection a2 is equal to x minus a1 union x minus a2. X minus a1 and x minus a2 both are finite set, so their union is also finite set. So that implies from the definition of the topology a1 intersection a2 belongs to tau. This topology is called cofinite topology. Why it is cofinite? Because the set A belongs to tau, that implies its complement must be finite. Next we go into the definition of comparison of two topologies. Let tau1 tau2 are two topologies on X, then tau1 is said to be weaker than tau2, or tau2 is stronger than tau1, or tau2 is finer than tau1 if tau1 is subset of tau2. So in discrete topology is the weakest and discrete topology is the strongest topology on X, and any other topology on X satisfies the relation in discrete topology is a subset of tau, and that is subset of discrete topology. Now we state the first theorem. Theorem 1, intersection of two topologies on X is a topology on X. Proof is, let tau1 and tau2 be two topologies on X and put tau is equal to tau1 intersection tau2. Clearly phi and x both sets belongs to tau, because phi and x both belongs to tau1 and phi and x both belongs to tau2 also. So their intersection obviously belongs to tau. For the condition 3, let a alpha belongs to tau for all alpha belongs to delta, where delta is a index set. Then union alpha belongs to delta a alpha belongs to tau1, and union alpha belongs to delta a alpha belongs to tau2. So union alpha belongs to delta a alpha belongs to tau1 intersection tau2. That means this is a common element, so that is equal to tau. So condition 3 satisfies. For the condition 4, let a1 a2 belongs to tau. Then a1 union a2 belongs to tau1, and a1 union a2 belongs to tau2, because tau1 and tau2 both are topology on X. That implies a1 union a2 belongs to tau. That means intersection of two topologies on X is a topology on X. Theorem 1 is not true if the word intersection is replaced by the union. From the following example, we get the required result. Let us choose the example. Let X is equal to ABC. That means a set consists of 3 elements, and we said tau1 is equal to phi x singleton A doubleton AB, and tau2 is equal to phi x singleton C doubleton BC. Then it is obvious that tau1 and tau2 both are topologies on X. Again, tau1 union tau2 is equal to phi x singleton A singleton C doubleton AB doubleton BC. Again, singleton A singleton C belongs to tau, and A and C are open set, and their union is equal to AC, but AC is not a member of the union tau1 union tau2. That implies the union of two topologies may not be a topology on X. Next we introduce another very important definition of topology, and that is called base or basis or open base. Let X tau be a topological space. A family script B of member of tau is said to be a base or open base or basis of the topology tau if every member of tau is a union of some member of B. For example, let X be a non-empty set and tau is equal to just simply power set of X. Then the family of all, we choose the family of all singleton is a base of the discrete topology on X. Next we introduce under which condition a family or a subfamily forms a base, and theorem 4 and theorem 5 gives the required answer. In a topological space x tau, a subfamily B of tau is a base of tau if and only if every open set G in tau and any point P belongs to G, there exists a member B, capital B, belongs to skipped B such that P belongs to capital B and that capital B subset of G. Then the subfamily forms a base. And theorem 5 gives a subfamily of subset of X forms a base for some topology on X if and only if B skipped B satisfies three conditions. First condition, phi belongs to skipped B. Second condition, X is a union of member of B. Third condition, and that is the final condition, give any two member of B1 and B2 in skipped B and P belongs to the intersection, that means B1 intersection B2, then there exists another member B3 belongs to skipped B such that P belongs to B3 and that B3 is a subset of B1 intersection B2. Next we introduce an example. The family of all open intervals along with phi forms a base for a topology on the set R, that is the set of all real number known as usual or Euclidean topology on R. Solution as let skipped B is equal to phi union all such open interval AB such that AB belongs to real number. Then condition 1 is obvious. Why condition 1 is obvious? Because phi belongs to skipped B and phi belongs to skipped B, so condition 1 is obvious by the theorem 5. From the condition 2, union n equal to 1 to infinity, open interval minus n to n is equal to R. So R can be expressed of union of member of skipped B. So R can be expressed as union of member of skipped B. For the condition 3, let B1 and B2 be two member of skipped B. Then B1 can be expressed as open interval A1 B1 and B2 can be expressed as open interval A2 B2, where A1 B1 A2 B2 all elements are belongs to real number. So B1 intersection B2 is equal to just nothing but the intersection of two open interval, that is A1 B1 and intersection A2 B2, that is nothing but maximum of A1 A2 and minimum of B1 B2, and maximum and minimum both are belongs to real number because A1 B1 and A2 B2 all elements are belongs to real number. From the diagram we get from the example maximum of A1 A2 is equal to A1 because A1 and A2, A1 is less than A2, so maximum of A1 A2 is equal to A2 and minimum of B1 B2 is nothing but it is equal to B1. Then from the picture we get B1 intersection B2, it is equal to just A2 comma B1, and A2 and B1 both are real number and that is it is a member of skipped B. So then from the theorem 5 we get the family skipped B forms a base for a topology on the set R. Next we introduce another theorem, and theorem 7, a topology tau 1 with a base skipped B1 is stronger than the topology tau 2 with a base skipped B2 if and only if for any member small x belongs to capital X, for x belongs to B2 belongs to skipped B2, there exists a member B1 belongs to skipped B1 such that x belongs to capital B1 and that capital B1 is a subset of capital B2. Consider the example 8. The family of all open intervals like closed A, open B, that means left hand side is closed, right hand side is open, where AB belongs to real number A less than B along with phi forms a base for a topology is called the lower limit topology of R, and it is stronger than usual topology of R. Solution is let skipped B is equal to phi union left closed right open a comma b, where a b belongs to real number. Then condition 1 is obvious because phi belongs to real number, because phi belongs to skewed b. For the condition 2, union n equal to 1 to infinity, left close minus n to n, it is equal to real number. So it is very simple, putting n is equal to 1, so it is equal to minus 1 to 1. If n is equal to 2, so it is minus 2 to 2, and so on. You get the whole real number r. So r can be expressed as a union of member of b. For the condition 3, let b1 b2 be two member of skewed b. Then b1 can be expressed as left close a1 and right open b1, and b2 can be expressed as left close a2 right open b2, where a1 b1 a2 b2 belongs to real number. So b1 intersection b2 is equal to, that is nothing but it is equal to maximum of a1 a2 and minimum of b1 b2, and maximum of a1 a2 and minimum of b1 b2, all elements are belongs to real number. So maximum of a1 a2 and minimum of b1 b2 lies in r. So then from the theorem 5 we get the family skewed b forms a base for a topology on the set R. Now we prove the second part of the example. Let AB be a open interval as a base of member of usual topology, and X belongs to the open interval AB. Then from the picture it is obvious that X lies in between A and B. So we get a base member close left close X right open B as a lower limit such that small x belongs to closed X comma B, and that is subset of the open interval AB. So theorem 7 applies the desired conclusion. That means the lower limit topology is the stronger topology than usual topology.